Okay, welcome back. This is the very last chapter from Mat 1140. This is chapter 18.1, Special Triangle Relationships. And I apologize for the extra S in the title there. Some of this will be a review. Again, it's stuff that we don't use a whole lot, so we tend to not remember. So we classify triangles by the sides or the angles. Okay, so we have three triangles that we talk about a lot. Oh, there's a fourth, and we're going to add that in. Why can't I make this a little larger? The first is an equilateral triangle. That means that all the sides are the same length. So when we go to mark this, or when you look at it, you'll see all sides marked with the same little tick mark. Just means they are all the same length. And that's what this top says, side AB. And so when I have no line over the top, it means that I'm talking about the physical measure, and that is the side from A to B. Equals BC equals AC. All three sides are the same length. In an equilateral triangle, because we'll talk about the relationship between the sides and the angles in a minute, it's also equiangular. Equa meaning equal. Angular meaning angles. Okay, but an equilateral triangle will have three sides that are the same length and then three angles that are the same size. It's isosceles if two of the sides are the same length, and the third is not. Okay. Again, the angles opposite those sides are going to be the same size. And then it's scaling if all three sides are different lengths. The longest side will always be across from the largest angle. Longest side. And when I say across, what I mean is if I draw a straight line from the angle, that is the side I hit. Longest side across from largest angle. Smallest side is across from the smallest angle, which means that middle side, whatever trapped in the middle, is across from the angle in the middle. Okay. The one that is not on here is the right triangle, which we will use a lot in the next section. And you'll see this little square, which means this is a right angle. If it has a right angle, then it is a right triangle. That's how we name them. Two triangles are congruent. That means same size, same shape, if all the corresponding sides and angles are the same size. So congruent means same size and same shape. If we laid them on top of each other, they would match up perfect. Okay. Determining the longest and shortest side, like I just mentioned above, if the three sides of a triangle are unequal, largest angle is always opposite the longest side. Okay. So identify the longest and the shortest. Here is my largest angle. 87 is bigger than 50 and 43. So C is my longest side. .43 is my smallest angle. So B is my shortest side. If I want two triangles to be congruent, and I'm going to try to draw this with a different orientation so we can make sense of what's going on here. If we're going to say DEF is congruent to ABC, that means that D and A have to be the same size. E and B have to be the same size. And F and C also have to be the same size. And notice how we have labeled these. Capital letters for the points, lowercase letters for the side opposite. So this will be lowercase d, this is E, this is F. Does not have to have the same orientation, just the same shape and size. Moving on to what we're going to use when we look at these in application problems, similar triangles have the same shape but are a different size. So think about what happens when we take a picture. We want everything in the picture to look like it does in the real world. We want it to have the same shape. It definitely has got to be a different size if it is going to fit into my 3x5 or my 4x6 photo. Okay. Ew, we should just, okay. Here's symbol for similar. Realized I forgot the similar symbol for congruent. Congruent means same shape, same size. So we got the equal with the squiggle over it. Okay, so there is the difference between those two. They are going to be similar if all the angles are exactly the same size, but the sides are in proportion, and the sides all have to be in the same proportion. Okay, now, let's take a look at what we have. I have two triangles. Both have the 105 and the 25-degree angle marked, and 2 out of 3 angles is all we need. Because all 3 angles in a triangle always add to 180, which means if this is 105 plus 25, these two add to 130. I subtract from 180, and this is going to be 50. The exact same situation happens over here. These add to 130, which means this has to be 50. So they're telling us they're similar, which makes sense. All 3 angles are the same size. And now I'm going to label what they give me. AB is 12 centimeters. BC is 26 centimeters. DE is 20.8. I want EF. This is the one I'm looking for. Okay. So the 12 happens between the 105 and the 25, and the X happens between the 105 and the 25. So I definitely have a relationship between those. The 26 happens between the 25 and the 50, and the 20.8 happens between the 25 and the 50. So the 26 has to go in the denominator. It's on the same triangle as the 12. So both of these pieces are the same triangle, which means the X and the 20.8 are also on the same triangle. If I want to solve for X, I am going to go ahead and multiply both sides by 12. Remember, the goal here is just to get x by itself. So whatever it takes to get rid of on the same side as the x, that's what we're going to do. So now I am multiplying 20.8 times 12. I get 249.6. I'm dividing that by 26, and I get 9.6 centimeters. Okay. Example 3 looks a little different. Tells me ABC, which is my big triangle. Let's see if I can. A, B, C. Is congruent to DEC, so my little triangle in here. DEC. Now, 1 and 2 have the same measure. They're similar, so we actually know that all 3 angles have the same measure. I do want to point out that a lot of times when we look at these, we kind of miss the fact that this angle C is the same angle in both triangles. Right? So in ABC, we've got that angle C, and in DEC, we've got that angle C. It's exactly the same. So they told us 1 and 2 are congruent. We've got C and C. I've got 2 out of 3 angles. We know that these are congruent. Fair enough? Even though they told us they were similar, we didn't really need to do that. So I have got to find the x, and I am going to set up my proportion here. I got x, which is that long side, over 10, which is the side opposite, angle D. Now I got to figure out how to write this other part. In my big triangle, this whole side is x plus 3. I still don't know what x is. I'm going to end up with a variable in 2 places, and I will just deal. When I add this side together, I get 10 plus 5, which is 15. Now I am going to multiply both sides by 10 to get rid of this denominator. I am also going to multiply both sides at the same time, because you guys are good at this, by 15, because that gets rid of this denominator. I can do these both at the same time. I get 15 times x, which is 15x, equals 10 times x plus 3, so 10x plus 30. So DC, because we're asked to find DC and DE. DC is 6. Yeah, we don't have any units on there, so I'm not worried about that. But now I got to find DE. And so to find DE, this side right here, we can label it DE or we can call it Y. I've got Y over, and I'm just going to stick it over this one, 8. Equals, I could use the big triangle, 9 and 15. I'd rather use the small triangle just because the numbers are a little smaller. And I have 6 over 10. Again, we're multiplying both sides of the equation by 8, because the goal is to get y by itself. 6 times 8 is 48. 48 divided by 10 is 4.8. So DE, which was the other piece we were asked for, is 4.8. Last one we're going to look at is an application problem, because a lot of times we can make sense of this when we think about what happens in the real world. Okay, so we are trying to find the height of a tree so that we can drop this tree and it doesn't hit a house, a car, a person, or fall into the street. The sun will make the same angle with any figure that it's shining on. Okay, so if we have a 6-foot pole casting a 4-foot shadow, while the tree is casting this 20-foot shadow, we can solve for the height of the tree. So x over 20 equals, let's see, height is x, and this one height is 6. So 6 has to go up here. My shadow is 4. Both of the heights are in the numerators, both of the shadows are in the denominators. And I'm going to show you a different way of looking at it. We don't always have to multiply. Sometimes we can find patterns in the numbers and have it all work for us. So if I take a look at this relationship, 4 times 5 is 20. That should be the exact same relationship I have up here. 6 times 5 is 30. The height of the tree is 30 feet. And if you want, solve the proportion the way we have been, making sure I'm correct here, and all is good.